Hey everyone, I'm Baffled by Reality, and today we're debunking a surprisingly persistent conspiracy theory involving the inverse square law and the moon. Now, this video by Taboo Conspiracy has been debunked previously, yet this deceptive troglodyte has continued to push it as fact despite some glaring and obvious flaws in his understanding of the math involved. Thankfully, this segment is pretty short, so let's go ahead and give it a watch.
I think it was maybe Jeranism or Globebusters or both who first mentioned this, but this is a terrific proof of the fake moon landings, and it deals with how much illumination there would have been on the lunar surface according to the heliocentric model. The inverse square law describes the intensity of light at different distances from a light source. Every light source is different, but the intensity changes in the same way, meaning this is a law for all light sources. The intensity of light is inversely proportional to the square of the distance. This means that as the distance from a light source increases, the intensity of light is equal to a value multiplied by 1 divided by d squared. Here are the simple equations. As an example, if you place a 100 lumen bulb in a floodlight that shines on only 1 square meter of surface, that surface will be lit at 100 lux. However, if you back the floodlight away to shine on 4 square meters, the surface is now lit with 25 lux. The full moon, which is supposed to be reflecting sunlight, has an illuminance up to 1 lux on the Earth's surface. That's not substantial, but a full moon has enough illuminance to read from it here on Earth. It is allegedly 376,285 kilometers to the moon, from Earth's surface to moon surface. Let's assume our Apollo astronaut is 0.01 kilometers, or 1 meter, above the surface of the moon. We now plug the numbers into our inverse square law equation to find the intensity of the moonlight at the surface, solving for intensity at distance 2. I have the numbers on the printout, but you can see for yourself the problem. Sunlight has an illuminance up to 128,000 lux on Earth. That's pretty bright. That's as bright as it gets. Assuming my math and figures are right, applying the inverse square law, the Apollo astronauts would have experienced 1,106,175,009,570 times more illuminance on the moon's surface than direct sunlight on Earth. Essentially, based on the inverse square law, at the moon's surface, the light would have been the most blinding light imaginable, and there should have been no photographs possible on the lunar surface.
So this all looks pretty legitimate until you think about it, like for just even a second. The only factual part of this video is the inverse square law. His explanation was basic but accurate. From a light source, the intensity of the light diminishes at a ratio proportional to the square of the distance it travels. To put it more simply, as the distance doubles, the light intensity decreases by a factor of 4, which looks like this. There are some caveats with this equation. First, you need to be measuring from an omnidirectional source. Focused light, such as lasers or using a parabolic reflector, doesn't work. So you can treat the sun as an omnidirectional light source. Second, this equation assumes there is no loss from absorption or scattering. Now, if you watched his clip, you might have noticed that his example breaks both of these rules. He assumes that the moon is the light source, which it's not, it's a moon. It's reflecting sunlight. And in his video, he mentions this.
The full moon, which is supposed to be reflecting sunlight,
and yet he still uses this number as his distance from the source. That's quite the lie he's trying to peddle. Now, if we wanted to actually find out how bright it is on the moon's surface, we would do it like this. So we have the sun, the earth, and the moon. This is the average distance between them. During a full moon, it is on the opposite side of the earth as the sun. So we go from sun to earth to moon. During a nice sunny day, we have an illuminance of around 110,000. I know he used 128,000. Most values range from 100,000 to 120,000, so I can guess he just saw a number and grabbed it without actually doing research. Kind of like how he grabbed that equation without learning how to use it. Anyway, we have our L1, our D1, and D2. And lo and behold, the illuminance on the moon is practically the same as it is on Earth. Or rather, it would be if the moon had an atmosphere, which it doesn't. You see, our atmosphere absorbs and scatters a pretty significant amount of light. On a nice clear day, you might be looking at around 20 to 25% loss. So we plug that into our result, and we found that the moon is actually a bit brighter than here on Earth. But wait, the straw man says. What about the full moon and it reflecting 1 lumen to the Earth? Shouldn't it essentially be the same as daylight since it's right next to the Earth? And to answer that, firstly, the actual number is 0.1 lumen. Again, he just grabbed numbers without checking anything. And more to the point, the moon is not an ideal reflector. It's very much the opposite. If it was a large planar mirror, we could in fact use the inverse square law, but it's not. The moon's surface is both incredibly rough and incredibly dark. It only has an albedo of about 12%, which is lower than most planets. Then many of you will notice that the moon is a sphere and not a plane. This means that not only is light being absorbed, it is also being scattered by a rough, convex surface. Using the inverse square law is not an applicable method for determining a luminance on the Earth from a full moon, or for determining the luminance on the moon's surface based on a full moon. But we should be able to use additional equations to do this. We know that the inverse square law works, and we know that you can use a planar mirror and it still remains applicable. Why is this? Well, when you view an object in a flat mirror, it is exactly as far away as it appears in the mirror. So when you view an apple that is 3 meters away from the mirror, it's going to appear as if it's 3 meters from the mirror in the reflection. So with the reflections and the inverse square law, we're not technically using the actual source for our distance, but the reflected source. Could we do something similar with a convex mirror? We know the distance to the sun, we know the size and shape of the moon, so let's pretend the moon is a convex mirror and use the mirror equation. The focal point of a spherical mirror is about half of the radius. The moon has a radius of 1,737.1 kilometers, so the focal point is around 868.5 kilometers. If we use the distance to the sun and the focal point, we can find the distance to the image of the sun. This turns out to be 868.5 kilometers. This is because as we approach infinity, the reflected image converges on the focal point. Now we know our luminance on the surface of the moon, our distance to the surface of the moon, and our distance from the Earth to the moon. Can we take this information and find out what the illuminance should be on the surface of the Earth? And before we get too far, we know that only 12% of the light is being reflected, so let's apply that to our L1. And then we put in our D1, our D2, and some math stuff. We can take into account that we're only getting around 80% because of the atmosphere, and look at that, we're right around what we expect to see, which is 0.05 to 0.1 lumens. So the next time you see someone spouting this kind of nonsense, you know how to tell them that they're wrong. I've been baffled by reality, and I'll see you around.